Hello everyone, welcome back to our tutorial. This is Qingyun. I just graduated from the University of Virginia and I'm now a postdoc researcher at Microsoft Research. In this section, let's look at how could we do exploration in non-stationary environments. Let's first recall this learning by exploration framework. In this framework, most of the solutions, including the ones introduced in previous sections, are making a stationary assumption about the environment, which means that although this environment is unknown to the learner, it is still fixed. But in practice, this assumption is hardly true and the learner is usually facing a changing or non-stationary environment. For example, I guess none of us can deny the dramatic changes happening in our lives because of COVID-19. Such changes may directly affect the reward this learner can receive from the actions. And now let's take a closer look at the learning by exploration formulation in non-stationary environments and see what could go wrong if we ignore the non-stationarity. As we introduced, in a stochastic learning environment, the reward of the actions are assumed to be drawn from particular reward distributions. The learning agent takes actions according to the historical observations collected and receive the reward correspondingly. We have introduced many good policies that can guarantee sublinear regret in a stationary and stochastic environment. However, in a non-stationary environment, those reward distributions could be changing over time. Here, let me use a concrete example from a real-world application to illustrate the existence of non-stationarity. So this figure shows the real-time click-through rate of 4 news articles on a dataset collected from Yahoo Today module. From this figure, we can clearly see that there are several dramatic changes in the news article's popularity, especially at the time points showed in the vertical dashed lines. In such a non-stationary environment, once a change has happened, the historical observations are no longer helpful or may even be misleading in the player's decision-making. If the learner cannot realize this and keep using the policy based on those historical observations, a linearly increasing regret can be inevitable. In order to avoid this, the learner needs to be adaptive to the potential changes in the environment when taking actions. And there are several different types of changes can be considered in non-stationary environments. One typical type of change is the abrupt changes, and the environment is piecewise stationary, which means that the changes happens abruptly and the environment remains stationary between two consecutive change points. And another change pattern is the gradual change, which means that the expected reward of the actions evolve gradually. This gradually changing environment is much more difficult because the changes may make the reward untractable unless more specific assumptions about how the environment is evolving are made. So in this tutorial, we will mainly focus on the solutions about piecewise stationary environment, which is a classical type of non-stationary environment. There are two main challenges of bandit learning in non-stationary environment. The first obvious challenge is that the changes, including when a change will happen and how the environment changes, are unknown to the learner. This challenge indicates that we may need to detect the changes in order to be adaptive. And the second main challenge comes from the fact that we have bandit feedback, meaning that at each interaction, we can only see the reward from the selected arm, which means that we only gain incomplete knowledge about the environment. How can we use this incomplete knowledge to do the change detection? It's very challenging. And just for your reference, change detection in the offline batch learning setting has been extensively studied in statistics and control theory, but there are not much study of it in the online bandit learning setting until recent years. Then let's move on to see the approaches proposed in the online blended learning setting in recent years. So according to whether the method is actively detecting the changes in the non-stationary environment, we can categorize the approaches into passively adaptive methods and actively adaptive methods. So the passively adaptive methods are actually not trying to detect the changes, but designing mechanisms to forget the old observations. The underlying assumption of this type of method is that older observations tend to be less relevant. And the active adaptive approaches design mechanism to detect the changes. They usually rely on assumptions on about the abrupt changes. So let's first go through several passively adaptive approaches. So the first set of methods include discounted UCB and sliding window UCB. In both methods, the learner is taking actions according to the UCB arm selection strategy, which has been introduced in previous sections. But the main difference is that here, when calculating the reward, empirical reward, discounted UCB incorporate an additional discount factor denoted as gamma here. So the reward observation will be exponentially discounted with respect to how old the observation is at current time point t. And the total count of observations is also discounted accordingly. And the confidence band is constructed using those discounted statistics. And similarly, in sliding window UCB, it incorporates a parameter, sliding window parameter called tau here. And when calculating the empirical reward, only observations in the most recent tau observations are used. And so does the count of the number of observations and the confidence bound calculation. So in both of the two methods, those algorithms are trying to be adaptive by forgetting the old observations. And these two methods are designed for non-contextual banded setting. So in the contextual banded setting, there is a method called weighted linear bandit, which shares the same spirit of the discounted UCB by adding exponential discount on the old observations. So the pros and cons of passive adaptive method are quite obvious. On the positive side, those methods are usually very simple without additional computational overhead. And all these three methods introduced before have provable theoretical guarantee on the cumulative regret in piecewise non-stationary environment. But there are also clear limitations of this type of method. So first of all, they are all assuming that older observations are always less relevant, which is not necessarily true in practice. And the second limitation is that those methods usually depend on proper setting of hyperparameters. For example, the discount factor and the sliding window factor is very critical hyperparameters in those methods. And in fact, they are very sensitive to those hyperparameters. This dependency on the hyperparameters makes the methods less practical. And now let's move on to the active adaptive approaches. Here I included a general framework to show the main components of an active adaptive approach. So comparing to the banded learning in the stationary setting, this type of method usually have some additional statistics about the stationarity or non-stationarity of the environment, denoted as capital Pi here. So those statistics will be used to do an online non-stationarity test. And after the once the change is positive, it returns a change alarm, and the algorithm will usually reset or partially reset its reward and also the statistics about the stationarity. Under this actively adaptive approach framework, different algorithms differ in terms of what test statistics are designed and also what exploration strategies are used. Here we briefly categorize the solutions according to what types of tests are they doing. So we want to emphasize that in this tutorial, we will only cover several typical ones of them, and there are actually a lot more being developed under this topic. And so let's get started with the method using cumulative sum test. To give the audience a brief background, cumulative sum test is a very classical sequential analysis technique originally designed by Dr. Page in the 1950s. Although we are more interested in the online bandit learning setting, let's first briefly look at how cumulative sum test is conducted in the offline learning setting to understand the basic concepts. So in this figure, the red dots are the reward observations we have. And from the observations, we can see that there is a clear change of reward distribution happened at 10.10. And let's use theta sub 0 and theta sub 1 to denote the pre-change and post-change parameters of the reward distribution. So the original cumulative sum test assumes that those pre-change and post-change parameters are known. And for each observation at a particular time point I, it constructs a log likelihood ratio of the observation using the pre-change and post-change parameters. And it looks at the cumulative sum of the log likelihood ratio. So the cumulative sum of it is set to be 0 at the beginning. And at each time step, it updates the cumulative sum by adding the log likelihood ratio of that observation, and then keep doing so over time. So according to the definition of log likelihood ratio, we can see that the expectation of this ratio should be negative before the change point, and should be positive after the change point. And based on this conclusion, this cumulative sum test looks at the difference between the current cumulative sum and the minimum of cumulative sum of log likelihood ratio. So over time, which is denoted as G sub k here. So G sub k should be 0 before the change point and will be increasing after the change point. So once its value is larger than a threshold, the test will report a change alarm. So this cumulative sum test has been shown to be effective in terms of change detection, but as I mentioned, it is originally designed for the offline learning setting, and it assumes the pre-change and the post-change parameters are unknown, which makes it not directly applicable to the online learning setting. So this work proposed a tailored cumulative sum test in Bernoulli bandit setting, where the rewards are drawn from Bernoulli distributions. The main intuition is that the absolute value of residual minus a constant epsilon, which is the minimum magnitude of change required in the non-station environment, has a negative mean drift before the change point and has a positive mean drift after the change point, similar as the log likelihood ratio. Since the expected reward is unknown, this method uses the empirical mean of the reward to approximate this expectation. And based on this constructed statistics, the algorithm monitors whether the cumulative sum of it is larger than a threshold or not. And it is worth noticing that this test is performed for each of the actions, and it requires that there are at least m observations for the tested actions. And this is to ensure that the empirical mean of the reward is a good approximation to the expected reward. And it depends on a threshold to do the change detection. So once a change is detected, it will perform a local restart on the detected arm, meaning that it will restart the reward estimation and the non-stationarity test statistic for the detected arm. And this solution is designed for Bernoulli bandit and piecewise non-stationary environment. And also related to the cumulative sum test, there are several recent work which propose to use a generalized likelihood ratio test to do online change detection in the bandit setting. Intuitively speaking, generalized likelihood ratio test is similar as a cumulative sum test, but it uses generalized log likelihood ratio instead of the exact likelihood ratio. In this case, the pre-change and the post-change parameters do not have to be known. And there are two recent work showing that generalized likelihood ratio can be used to do effective online change detection with bandit feedback. And it is able to handle both Bernoulli reward and the Gaussian reward. Another change detection method proposed is online mean shift detection. It is proposed in this monitored UCB algorithm. So the method is quite intuitive. It compares the running sample means in two segments of a sliding window. So in this figure, the blue vertical lines shows the two sides of the sliding window, and the dashed line is the middle point of the sliding window, which separates this window into two consecutive segments. And then it calculates the empirical reward of these two segments and compare the difference. If there is a change point, the difference should be large. So if the algorithm observes that the difference is larger than a threshold, a change alarm will be reported. Differently from the previous algorithm, this method do a global restart, meaning that it will restart the related statistics for all the arms once a change is detected. And it is worth noticing that in addition to the UCB arm selection strategy, the method also needs to periodically do uniform arm selection, such that sufficient observations can be collected to perform the change detection. So all the methods introduced before, except the weighted linear bandit, consider the non-contextual bandit setting. Now let's look at a confidence bound-based change detection method developed for the contextual bandit setting. So the intuition of this confidence bound-based method is that if the environment is stationary, the reward prediction residual should be bounded. And more specifically, in the online bandit learning setting, the bound on the residual should be related with the confidence bound of the reward estimation from this particular bandit learner. And if the environment is stationary, presumably the residual should follow this inequality. Otherwise, we will consider them as unexpected outcome, which can only be caused by two reasons listed here. So one reason is that there are something wrong in the observed reward, which can only be caused by large noise. And in a stochastic environment, we can actually exclude this possibility because the probability of observing large noise should be small. And the other reason is that there is something wrong in the predicted reward, which indicates that the model is incorrect or the model does not fit the current environment. And in this case, this unexpected outcome can be considered as an indicator of the non-stationarity in the environment. Based on this intuition, a prediction bandit concept was proposed, which is basically measuring whether an observation is unexpected or not for a particular contextual bandit model. And the estimated bandwidth of a particular contextual bandit model is calculated by considering the bandwidth bandits observation over a sliding window. And similarly, similar as the previous solutions, a threshold is used to help decide whether a change is detected or not. So if the bandit is larger than the derived threshold, the learner of this contextual bandit model will be abandoned, and a new one will be created accordingly. And this solution can actually do the test on the other side, in which a more strict threshold can be used to decide whether a learner is good enough to be used. So if no learner is good enough, a change will be reported and a new learner will be created. By using this confidence-bound-based change detection, this work proposed a hierarchical bandit learning framework, where the algorithm starts from a single learner and makes decisions using a knowledge learned by this learner. And based on the observations collected, it monitors the prediction quality or the prediction bandits of this learner, and it adaptively creates new learners if needed. For example, if the environment has changed. And at each interaction, it selects the best learner to use for the current environment, according to the test introduced before. And the observations collected at each interaction will be used to update the reward estimation of the selected learner, and also the bandits estimation of all the learners created. So by doing so, this algorithm is able to adapt to the changes by creating new learners and selecting the best learners that can fit the current environment the most. Under the confidence-bound-based change detection framework, a follow-up work considers the detection of context-dependent changes. It first recognized that under the contextual bandit formulation, the changes on actions reward are also context-dependent. Let's see, in a piecewise stationary environment, by performing the non-stationarity test introduced in previous sections, the bandit algorithm is able to create bandit learner at different time points. But if we look at the reward on those actions, we can find that because of the change on the environment parameter, there are indeed reward changes on some of the actions, which can be called change sensitive actions. But at the same time, there can also be some actions whose reward will not change. For example, if the context is orthogonal to the change direction, then there won't be changes on the reward. And this type of actions can be called change invariant actions because they will not change. The reward of them are not changing. In this case, the old learner's reward estimation for those change invariant actions are still accurate. And based on this intuition, this work proposed to reuse the knowledge learned in an old learner for those change invariant actions, such that unnecessary exploration can be saved. So with those solutions introduced, here I would like to introduce a little bit about the empirical evaluation for non-stationary bandit learning algorithms. Since the online deployment of bandit learning algorithm is usually not a feasible option for everyone, here I will mainly focus on the offline evaluation. So the offline evaluation of bandit learning methods are notoriously difficult, and the evaluation of non-stationary bandit methods are even more challenging because the non-stationarity may not exist in an offline dataset. Here I briefly summarize the evaluations into 3 categories. The first type of evaluation we can do, which is also the easiest one, is to use simulation. Basically, you can simulate everything about the environment. For example, you can simulate different types of changes and different magnitude of change. Because of the full control of the environment, this type of evaluation can be used to illustrate the effectiveness of the non-stationary method when the required assumptions are satisfied. But in order to show a non-stationary bandit solution is practically useful and the assumptions are not unrealistic, evaluations on real-world datasets are usually appreciated. For example, an ideal real-world dataset is the Yahoo Today module dataset, because unbiased evaluation can be performed on this dataset, and it also shows certain levels of non-stationarity. However, such ideal real-world dataset is quite rare, and in many cases, the dataset may not have any non-stationarity because of the data collection. In this case, although not perfect, a feasible or possible option is to simulate the changes in the real-world dataset. Now let's take a brief look at the theoretical analysis in terms of regret bounds of the non-stationary banded solutions introduced in this section. First of all, to obtain those regret bounds listed in this table, different assumptions are needed in different methods. But overall, they all require the environment to be piecewise stationary. Although in different forms, all of them have a detectability assumption and on the magnitude of the changes. And in this result summarization, gamma sub t is the total number of changes up to time t in a piecewise stationary environment. And for from this result summarization, we can see that currently the best we can achieve is a square root of gamma t times t, which actually matches the lower regret bound in a piecewise stationary environment. But in order to achieve it, the methods usually require the total number of changes to be known beforehand. In addition to the theoretical analysis for piecewise stationary environments with abrupt changes, this following work is able to prove sublinear regret even when the environment is slowly drifting, as long as the total variation is bounded. Here, C sub t denotes the total variation of the reward distributions over time up to time t. And it is worth mentioning that in this two work, they analyzed their solutions with different notions of regret in different types of non-stationary environments, including interval regret, switching regret, and dynamic regret, which provides a comprehensive way to understand the theoretical behavior of non-stationary solutions. To summarize, being able to handle non-stationary environment is very important for bandit learning algorithms, and there are a lot of emerging work under this topic. And here I would like to conclude this section with several open questions according to our research experience on this topic. So the first question is, in addition to simply detecting the changes, can we also identify the related historical observations and efficiently reuse them? Answering this question will help us to handle scenarios where we have recurring environment. For example, because of seasonal changes, the new environment might be the same as an environment in the past. And another example is the context-dependent changes mentioned earlier. Secondly, as you may notice that most of the current studies about non-stationary bandit learning focus on the piecewise stationary environment. And usually they have various detectability assumptions. So how can we relax those strong assumptions and better handle gradually changing environment is worth studying. And finally, non-stationarity is also very common in applications where reinforcement learning is used. However, research about reinforcement learning in non-stationary environments is very sparse. So it is another research topic worth exploring. And this list include all the references mentioned in this section. And thank you very much for your attention.